3 part A, then it says, right, this is what it says on the diffraction grating, that there are 3,500 lines per metre, and it wants to know what the percentage uncertainty in that number is. So this is the kind of question that you don't want to overthink and start thinking, oh, well, how did they measure it? You know, wouldn't it depend on the accuracy of the instruments they use and all this kind of stuff? All you're doing is just saying, right, let's look at this number, and you can see it's given to the nearest 0.1. In other words, the resolution is 0.1 times 10 to the 3 lines per metre. Because the fact that it's only given to one decimal place there implies that we don't know it any more precisely than that. So the resolution is 0.1 times 10 to the 3 lines per metre. And that's equal to the absolute uncertainty. In the value. So to get the percentage uncertainty, we just say that that's equal to the absolute uncertainty divided by the value measured times 100. Okay, so that's equal to 0.1 times 10 to the 3 divided by 3.5 times 10 to the 3 times 100, which works out as 2.9% is our uncertainty. So part B just wants to know, if you've got that many lines per metre, what the spacing between each individual line is. So basically you can see that's just given by that the spacing, which is d, is equal to 1 over 3.5 times 10 to the 3. Because if your total width is 1 metre and you've got that many lines in it, then each one of them must be 3.5 times 10 to the 3th, as it were, you know, that fraction of it. So it's just 1 over that, which comes to 2.86 times 10 to the minus 4 metres. Yeah, but you have to be very careful, because on the answer line it asks for the answer in millimetres, so you've got to convert it, and remember that a millimetre is a smaller unit, it's only 1,000th of a metre, so you're going to have 1,000 times as many of them. So you have to multiply by 1,000 to get the number in millimetres, which is 0.286 millimetres. However, because the number we put into that was only known to 2 significant figures, then we can only know the answer to 2 significant figures, so that's 0.29 millimetres to 2 significant figures. So it then wants to know the absolute uncertainty on that number. And again, that's a difficult thing to work out rigorously, but we just go by working it out from the resolution of the number we've put down and say, well, that's correct to the nearest 0.01 millimetre. So the absolute uncertainty, which is what it asks for in the next part, is the resolution, which is 0.01 millimetres. Okay, so in part D it gives us this pattern and asks us to find the distance between 2 adjacent maxima on the in the pattern. So what you don't do is just look on the ruler and measure that distance, because if you do that, it's going to have a really big uncertainty because of the limited resolution of the ruler compared to that gap. So what you do is you try to measure, remember, as big a number as you can, because that minimizes the percentage uncertainty. So ideally the thing to do is count the total number of maxima there, and you find that there are 26 maxima if you count all the way through there. If you have 26 maxima, if you think about it, if you have 2 maxima, you have 1 space. If you have 3 maxima, you have 2 spaces. If you have 4 maxima, you have 3 spaces. Okay, so 26 maxima means that we have 25 spacings. Okay, so what we can do is therefore just measure the total separation between the first one and the last one, and divide it by 25 to find what each individual spacing, and that's going to give us a much better number than just trying to measure between 2 of them. So if you do that, you find that this one comes out about 0.6 centimeters, this one comes out about 13.6 centimeters. So you get that the spacing is equal to 13.6 minus 0.6 divided by 25, which is 13 over 25, which is 0.52 centimeters. And again, notice how they're trying to catch you out, because on the answer line it wants the answer in millimeters. So you've got to make sure you notice that and realize that a millimeter is 1/10 of a centimeter, so it'll be 10 times as many millimeters. So times 10 gives you 5.2 millimeters is the spacing. You could have done it with fewer than 26. You could have counted, you know, whatever number you wanted, but don't do it with too small a number. I think if you had fewer than 10, they would say you're not making the best use of the data, and so the sensible thing is use the whole lot. So for party, it's useful to do a picture, I think, of what you've got. So this is the setup. So this is where the diffraction grating is, and it tells you in the question that there's then 2.5 meters to the screen where the lines are being observed. And we know from this pattern that the distance between the 0 order image, the central one, and the 25th order image is 13.0 centimeters. Okay, so that's n equals 25, and that's n equals 0. So what we can therefore do is to say, right, this, oops, sorry, I'm drawn that very well, but you get the general idea, that is the angle theta for the 25th order image. Right, because if this is the 0 one, there are 26 lines altogether. If that one's 0, this is 25. So make sure you've always got to be careful with that 25, 26. But remember, if one of these is the 0 one in the middle, then this is going to be the 25th order one if it's the 26th line in the pattern. So that's our setup. And so we can just say, right, this is a right angle triangle. So tan theta is equal to 13.0 centimeters, but let's put it in meters, because remember these have got to be in the same units. So let's do that now and put this and say 13 centimeters is 0.13 meters, right, because there are 100 centimeters in a meter, so you just divide that by 100. So tan theta is equal to 0.13 divided by 2.50. Okay, opposite over adjacent, which comes to 0.052, which means that theta is the inverse tan of that, which is 2.98 degrees. So now we can use the normal equation we use for the diffraction grating to find out what d is, which is the spacing, which is what the question wanted us to find. So we have n lambda is equal to d sine theta. So n lambda over sine theta is equal to d. So we can put the numbers into that. So n is 25, because this is the 25th order image that we're measuring theta for. So it's 25 times lambda, it told us was 628 nanometers, so that's 628 times 10 to the minus 9 meters, divided by sine of 2.98 degrees, which, if you work it out, gives you 3.02 times 10 to the minus 4 meters. So that's equal to d, which, because they ask us for the number of lines, implies that the number of lines, which is equal to 1 over d, is 1 over 3.024 times 10 to the minus 4, which works out as 3,300 lines per metre. So then in part F, it wants to know whether the value that was claimed for the number of lines, okay, which was 3,500 lines per metre, whether that's consistent with the experiment. So remember, we decided that the uncertainty was 100 lines per metre. Okay, because you can see the resolution of that is to the nearest 100, so the uncertainty, the resolution, is 100 lines per metre, which means that the experimental value should be between 3,400 and 3,600 lines per metre. And it's not. It's 3,300. So it's not, which means that it's not consistent. Okay, so although the number is not too far away, it's nevertheless not within what the experimental uncertainty we estimated for the diffraction grating suggested it should be. But of course what we haven't done is taken into account any of the uncertainties in the experiment, so it may well be that really it is, once you take that into account, but based simply on the resolution of the number given on the diffraction grating, it's not.